Automatic.
Great.
That's recorded. I can't tell you how many times I forgot to start the recording.
Yeah, we have a bad track record on that one.
Also, we don't see anybody. You'll just, here we go. We have some
Yep.
people are rolling in.
Attendees, good afternoon, everybody, and welcome to our ESRP Learning Program webinar. We are here with Dr. Eric Grossman, and we will get started in just a few minutes.
Guess I could have had some theme music from our Muddy Blues band.
Jay and I can burst into song from our choir.
We could. We've been talking about it. There's 3 DFW people in our choir. We just need a tenor, and we got a quartet. We actually know who it is too. We're trying to recruit him.
Trying to headhunt him.
Now I'm worried we're telling people out in public and they're going to ask us for performances.
Absolutely.
We definitely need like hold music to entertain our audience while we're waiting for the time to start.
That'd be fun.
Welcome, everybody. We'll just get started in a minute here, but we are happy to share this Tuesday afternoon with you with our ESRP Learning Program webinar.
I'm excited for it as well, Eric. I remember our kickoff meeting at the refuge long ago, back in the early days when Tish just started and talking about this project and getting it going. So looking forward to it.
Definitely exciting to see all of it come together. And we're excited to be supported by you guys.
All right, we're going to get started. Welcome, everybody. My name is Tish Conway-Krenis, and I'm the Science Manager for the Estuary and Salmon Restoration Programs Learning Program. And I'm here with Jay Krenitz, who is the ESRP Program Manager, and our speaker today, Dr. Eric Grossman with USGS. So I will give the reins to Eric in just a minute, but I'm going to show a couple slides to introduce him. So he's going to be talking to us today about restoring sediment supply to sustain Delta marsh, numerical modeling of sediment transport and flood exposure to support adaptive and resilient restoration investments in the Nisqually River Delta. And you, I think most of our audience is aware, but the foundation of ESRP is the Puget Sound Nearshore Ecosystem Restoration Project, or PSNRP, which generated a whole bunch of really great white papers to help us articulate the extent of the damages to the shorelines in Puget Sound and what can be done to restore them. So really trying to infuse the restoration work we do with a science foundation. And we have kept this concept alive with the ESRP learning program, which funds work that really supports science work, research projects that really support the planning, implementation, design of restoration projects. And the work that you're going to hear about today from Eric is a really great example of that. Sediment supply and transport is one of the processes that we seek to restore a lot in our process-based restoration program. And so it's a really important one. And it's exciting to get insights into how those processes work. I just wanted to put a shout out to the link to the wiki page that Eric has developed, which is the place that we will put the link to the recording of this webinar, as well as links to all of the reports and materials that are generated from this project. So it's under development, I would say, but it's a place to check back for later. And then just to remind you, we see this as sort of all part of the cycle of learning and assessing and implementing to help connect science and restoration through our work on the science and practice arms of ESRP. And then with that, I would just like to introduce Eric. Eric, we are so excited about this work today. I know this has been a long time in coming and such a great accomplishment. So as many of you know, Dr. Eric Grossman is a coastal and marine geologist with the U.S. Geological Survey Pacific Coastal and Marine Science Center, who leads the USGS Coastal Habitats in Puget Sound project and co-development of the USGS Coastal Storm Modeling System, COSMOS. Eric's research and recent publications examine coastal geomorphologic and habitat response to climate and land use change with a focus on nearshore sediment dynamics and disturbance thresholds important to habitats and the people who depend on them. So really exciting stuff, and welcome, Eric. And I will let you take it away. I will just invite folks while Eric is talking and you have a question, you can go ahead and put it into the Q&A, and we will make sure that he has a chance to answer them at the end of his talk. There should be plenty of time for questions and answers.
Thank you, Tish and Jay. Does this show up fine, and is my volume okay?
Yes. Yep. You look great.
Great.
And we see you and hear your slides.
Well, thank you everyone for coming. And I'd like to start by acknowledging a fantastic team of scientists that I get to work with and that have contributed greatly to this work. I'd also like to acknowledge the Coast Salish people. We're all on their lands, and in particular Nisqually tribe and staff that I've been fortunate to work with over the years. Fantastic people. And in particular, I want to call out and honor Billy Frank Jr., who I was so lucky to have some amazing conversations with. He really understood and argued that in order to restore so many of the degraded coastal habitats across Puget Sound, some really critical barriers to restoration needed to be addressed. And these barriers, are what to do about flood protection and other urban infrastructure, levees, dikes, roadways, like you see here with the Interstate 5, and address public will to go about restoring. And I find myself now, several years into this kind of research, hoping to help inform that process. I really want to acknowledge the ESRP for funding the majority of what I'm going to talk about today, as well as leverage with Nisqually Tribe and the Fish and Wildlife Service, the Nisqually Refuge, and a lot of support from Northwest Indian Fisheries Commission over the years and EPA. And I'll just draw your attention to the Browns Farm restoration, where About 5 miles of dike was removed in 2009. And you can see by the colors in the photo, this bare brown surface is what we're concerned about with reestablishing marshes that are critical for salmon. And this Interstate 5 built on a filled causeway that essentially covers 87% of the sort of floodplain area where the river and distributaries try to flow out to the sea. And so an unconventional outline, I'm going to talk today mostly about the ESRP study, where we examine the sediment budget, the delivery from the river, how it moves through this system, how much flux is in, how much exports out and is therefore retained, how much gets lost, and what a couple of alternatives might be able to do to help restore that sediment to this system. And then I'll talk briefly about a second modeling study looking at projected changes in the exposure of this entire floodplain, the infrastructure, and the restoration investments in 2009 to higher sea level and stream runoff. And as part of that, we'll look at the vulnerability and the influence of the I-5 causeway on flood exposure and opportunities to reconnect the river through some of these areas, which may in fact enhance resilience and ecosystem functions and reduce the overall flood exposure. And so some take-home messages that I hope you'll come out with is that our findings of the sediment budget are that there's a fairly small amount of the fluvial sediment load that comes down to Puget Sound is actually accumulating inside this restored estuary. And because of that small amount, it's going to take a lot of time to recover the elevation grade and the marshes to be able to develop like we see outside of the restored area here in these green colors. If all of the sediment coming down the river could get into and be retained within this system, it would still take about 18 or so years, given our assessment. And the other thing, or the real reason why this is the case, is that waves really matter. They cause a lot of resuspension and redistribution and interact with the currents. And in this case, a lot of material gets, in fact, exported out and lost offshore. And then lastly, large flood events already affect the floodplain and the system. And what you're going to see is that there's some exciting opportunities here to reduce that flood exposure and help address the sediment supply concerns in the investment. So 4 quick things: sediment matters, the budget, the amount, the way it moves through the system, and the composition or type of sediment matters. Where restoration occurs and maybe the timing of putting different strategies in place really matters. The barriers to restoration, in fact, can be fantastic opportunities, and waves really matter. So quickly, some background and concern for those who aren't familiar. This was a thriving estuary back in the day, and it was converted in the early 1900s with building a 5-mile dike system that you see in this dashed line, and converted to a bunch of other sort of land uses. That cut off sediment supply, and then the activities we think led to some subsidence. I'm not sure how long it took. David Trout and Chris Ellings can correct me, but I want to say it was 30 to 40 years in the making before 2009 to actually get public support and the capital costs to put in the actual restored estuary and remove all these dike systems and help recover the environment, which you can see here with these lowered outer dike channels helped out by cutting down. And that's where we are today with this restored system, and a number of central papers, including these here, have shown some amazing successes in many metrics and desired outcomes of the restoration. But there's this lingering concern with the sediment supply. And a colleague of mine helped to quantify just how much sediment gets trapped way upriver at Alder Lake, and has computed that there's enough sediment trapped behind the reservoir since 1945 to be equivalent to about 74 to 90% of the total load that could have made it down to the Delta. There's a lot of material is getting trapped and slowly filling up Alder Lake. And so the project objectives were to advance the predictive model capacity and our understanding to assess whether or not enough sediment below Alder Lake is sufficient enough to recover the Delta's marshes if more of it could be routed to the marsh. We also wanted to understand whether delivery of sediment was important and how important to regain between 1 and 2 meters of subsided grade to then get the elevations up to a suitable location for vegetation, the marsh vegetation, to really take off and succeed, start trapping sediment, start sort of keeping up with sea level rise. We also wanted to ask the question of whether or not full breaching of these channels that you see here cut through the old levee or dike, whether breaching them all the way down to the bed of the neighboring channel systems was required, particularly along the river, or can costs be saved by just simply notching a little bit down, allow water to flow up and over, and maybe everything would evolve and sort of progress well. Fourth item we wanted to do is look at whether or not some of these restoration options may in fact help reduce flood hazards and help flood management by reducing water levels and flood risk today and into the future. And then hopefully get to a point where all this quantitative information and lessons learned could help inform sort of nuances of restoration guidance. And restoration guidance for estuaries is largely derived from kind of experiences on the East Coast with Chesapeake Bay and other locations. And some seminal work has laid out a very nice sort of path forward. And I think what we're learning now with some of the sort of more quantitative research about hydrodynamics and sediment is that we can really start to address a little bit more predictively what to expect for the extent of success in these restoration projects, the rates of achievement or recovery, the timing that the outcomes might sort of reach those successful states. And with these tools and knowledge, we'll be in a better position to measure the performance of these investments. We might reduce the capital investment costs in the end because of less adaptive management, and helpfully garner public will to restore our ecosystems. So just a couple images here. I often have a lot of material on my slides, but I'm going to point to the salient parts of some of these more detailed slides. But just to orient you, there's been several other earlier phases of restoration that have been doing quite well. They're on the right bank of the river. You can see here that there's a lot of green colors indicating marsh cover, distinguished from what's happening inside the newly restored area. But these marshes out here, you can see also are sort of at these elevations shown on the right panel with yellows and light blues that are much higher than the majority of this platform in here that's been subsided, and you can see with the darker blue colors. And so we're going to be looking at this system, and one of the areas where some identified restoration was sort of suitable to all parties, wouldn't conflict with other infrastructure and assets, and examine just what we can learn from modeling and detailed research of hydrodynamics and sediment. And we did this primarily by developing some models, some numerical models, primarily using Delft3D. These are two-way coupled models between these larger regional South Puget Sound and Tacoma Narrows, forcing a much finer model right in the Nisqually area that you can see here. We have all the important boundary conditions, new elevation data, water levels from measured tides out at the NOAA gauge, river discharge from US stream gauges, as well as projections in the future from the University of Washington Climate Impacts Group. The free surface, meaning atmospheric pressure and winds over the domain, are prescribed with a very high resolution weather product from the Canadians, and they can also take observations at nearby stations, which we use for waves and future projections. And the sediment is derived from largely this study. The way we developed the modeling design and approach was 3 different types of simulations. 2 quasi-realistic type models. So these are like measured conditions in our recent past, one without sediment in the model to begin with, and one with sediment on the bed. And what this allowed us to do with the no sediment is track the direct transport of fluvial derived material coming through over several months and identify where it's predicted to accumulate. And then with the sediment on the bed models, look at all the contributions of processes and available sediment on the bed to be redistributed, fluxed in and out, and accumulate in this accumulation polygon. All of this activity sort of through indirect is largely across this northern boundary, but some occurs sort of at the lower parts of the river. And then I'll come back to, in a minute, the approach we use for the schematized models to examine the restoration alternatives here. And then for reference, you'll see 10 observation sites where we measured all kinds of things, time series of water levels, currents, turbidity, water quality parameters, and then made extensive cross-channel measurements to characterize all of the variability and develop models to calculate the mean flows, the discharges, and especially a time series of suspended sediment concentration based on turbidity. And all of these approaches are summarized in a recent paper that Dan Nowacki and I put out for Port Susan Bay. Now, this characteristics of the sediment are pretty detailed. I'm just going to point out the salient features here for you. You can read the report for all the real details, but we prescribe sediment coming into the model at the bottom here of these panels with the known sediment concentrations from a previous study of ours, as well as this study. We've included 3 particle size classes, half of it's fines, muds, half of it's sands, based on what Chris Curran and I have found over the number of years of examining the river sediment coming through and the material on the bed. And we include a number of sort of key sort of traits of sediment transport, including the cohesive nature. But you can imagine, and I hopefully, if you don't know this already, sediment is very complex and variable, and it varies in the water coming through the river, it varies in the estuary, it varies on the bed considerably through space and time. And so to capture that variability and our uncertainty, we chose to bracket 2 critical sediment transport properties: the critical shear stress for erosion, that's sort of talking about the erodibility of material on the bed, versus the settling velocity that sediments fall out of the water column at. And the top approach is sort of characterizing the most erodible and most mobile, that would be really moved around easily by any types of energy. And the bottom one is sort of the least erodible and least mobile. And so you'll see these referred to as R1, 2, 3, and 4. Don't worry too much about it. I'm going to point to the salient features here. But we also were able to initiate the bed based on an approach to get at sort of a long time period, 200 months, and starting with a thick enough layer of sediment on the bed that all these processes that we know about will sort of work and redistribute it where it's sort of in some semi-equilibrium with the conditions. And this is an approach that we've followed from colleagues of ours in the Netherlands. And in a few places, enough scour occurred, suggesting there's plenty of energy to move these materials, that they were filled with coarse sand. And lastly, for the model alternatives, we chose sort of a reference system that's exactly today and a few different channel connections here off of the river at a site called NR2, and largely varied these by the length or connectivity to this other distributary channel, old distributary channel, and depth, mimicking the slope from the bed of the river to the average depth of this channel here to have flow connectivity. And this is trying to answer the questions of how sensitive all of this is to slope and hydrologic connectivity. We included 4 stream discharges, daily and annual flows, essentially, the 2-year and 5-year floods, 2 sea level positions, today's, and 1 meter of rise, and those sort of 3 sediment classes for all 4 configurations. And we developed a number of interesting metrics. I'm not going to go through them all, but trying to understand the sediment transport through these and the efficiency to which these channels would convey material and route it from the river to the restored area. Briefly, the environmental conditions during our study were kind of average. We had maybe slightly more runoff and sediment delivery in the first winter than the second year. And during the winter, it was very important that we had a period, perhaps with fairly low river flow shown in the middle panel, but a lot of waves, and waves from different directions, mainly the north gales versus the south gales. And then you'll see in this later period, just for reference, we had a really nice sort of river flood, presumably with sediment. These typically are occurring with southern winds. The model looks like this. Many of you have seen animations of different types of models, and this is getting straight to the suspended sediment transport for one of the model configurations. One of them that we feel sort of a little bit more confident represents the system best. But you'll just see quickly, like when we had some river flow and sediment here, these yellowish colors with high suspended sediments show up. They relax as the river goes down pretty quickly. And you'll also see that a lot of that yellow is sort of directed out here offshore. And inside the restoration area, you see some connectivity only on these sort of second flood tides of the semi-diurnal tide cycle. And really, we only see appreciable sediment when the river's pumping material in there. And I'll leave that for just a second more, so you can kind of see this build up in flow, build up in the sediment coming down the river here. And then it's sort of cycling in. So for validation, we had a number of stations and overlapping periods despite a lot of vandalism to our equipment. And our water levels computed in blue versus measured in black are really pretty well dialed in, average errors of 3 to 5%. Similarly, with current velocities, a fairly low average error. There was one site here at NR2 in the river that was, our model is biased a little low. But we think that it has fairly little influence on the overall results, because you get these highest currents when the water is sort of ebbing reducing from its high tide. Down below the levee elevations and the platform elevations, when all of that flow is directed offshore. And similarly on the flood tides, when you get up to a high tide, the current speeds are really decreasing rapidly, and there's very little sort of potential for moving material. For the suspended sediment concentration, comparison to observations here, these are for the 4 different model configurations. And for one of our sites up near the inlets along that north boundary, bringing material in and out. And this is sort of the longer record, and this is a blow up of just one of these weeks. And you can see how these configurations of most erodible and mobile versus least erodible and least mobile vary with respect to what was measured. And overall, this is really tricky to do, but we think that we're capturing a lot of the important high variability with this R2 configuration and doing really well with the low variability with this R3 comparison, particularly given that these numbers are really low. And at a different site where it's more dominated by sands, the R4 configuration really captured sort of the base level of suspended sediment concentration over time. But even so, there's so much variability and uncertainty that we're going to be using all 4 and bracketing the range and developing estimates of the flux from all of the composite range. And then lastly, in terms of sort of details, we wanted to answer whether when sediment is coming down the river, is it well mixed or pretty stratified only at the surface, such that it would help influence any decisions about restoring the levees that are shown here, breaching all the way down to the bottom, or just notching a little bit and letting, potentially high suspended sediment concentrations only at the surface, letting them in. And that's what this shows. These 3 days of fairly high flow when there was actually sediment in the river. Most of it was very uniform with depth, well mixed at the surface, midwater, and bed. A few sort of initial outputs of the model show that the marsh platform inside this polygon here is inundated sort of between 30, 35, and 45% of the time. This is very consistent with previous assessments made over the years. And then the mean flow showed some really kind of exciting, interesting patterns with this clockwise sort of flow in dominated through McAllister Creek and flow out through all of these distributary outlets. And this is sort of mean conditions over time. For the sediment accumulation projections that we came up with for the winter simulations, when there was in fact some signal of sediment coming down the river, we found evidence of somewhere between 0.3 and 0.6 centimeters of accumulation over this sort of 2-month winter period. And if we focus in on the sort of R2 and R3 scenarios here in the middle panels, you can kind of see that pattern that you might start seeing in a few more of these map outputs. Reds and peaches are sort of accumulation and blues are erosion. And then for the summer simulations, we saw a whole lot less down here in the few millimeters and really sort of blunted. And then for the residual or the mean average transport of sediment, it follows generally this clockwise pattern, and I'll just focus you in on these sort of middle panels where the white arrows are. It really follows the sort of flow in through McAllister, a little bit of flow in when the water levels are high enough out here at this little bend, and a flow out on average across this entire north boundary. This is sort of the exciting part, is when we put all this together to start looking at the budget. These are the 4 configurations, R1 through 4. In the blue line is what the input of fluvial sediment is over the model runs. And this is just for the direct transport without any sediment on the bed, really tracking just where the fluvial dry material goes. And only 2/3 stays in the model. Some of it's being exported far offshore. In the delta itself, so the tide flats is this orange color, yellow color, and then the amount that is sort of accumulating, computed to accumulate in the restoration area is these red lines. And you can see from these sort of R2 and R3, it's a fraction of what's coming down the river. Again, this is only for material being affected by currents and the river flow over the course of a few hours to a few days. Whereas this is the same scaled plots here, cumulative mud transport up to 15,000, and with the sediment on the bed for winter on the left versus summer on the right. And what you can quickly see is that for this very mobile sediment configuration, where actually the model computes a fair amount of loss of sediment offshore, especially in winter when there's a whole lot of material coming to the system. And then the R2 and R3 configurations that we have a little bit more, or feel are capturing conditions a bit better, are characterizing the accumulation in the restoration area in this purple color, kind of similar to what we see with the direct, but scaled a bit more. And that additional amount in winter is due to the effects of waves that I mentioned. And you can really see that expressed by the difference here in the outputs during summer, when there's just no appreciable sediment coming down the river. And all of this movement and material getting into the system is really due to just the waves. So this is pretty exciting because we always suspected this, and we've worked on it a few different times, and it's coming together now in these studies. This is geologists and oceanographers. We love our swiggles and lining up wiggles, but I'm just going to direct you to these two bottom plots primarily. This row here is the direct transport in winter and summer that we just saw, but through time. And what you can see relative to sort of the winter loads scaled here in whole numbers versus the vertical scale in the summer, 1/10 less. There's a whole lot more sort of material direct transported in the winter, and it's much higher than in the summer. And then down below, with the sediment on the bed and all the processes redistributing material, the indirect transport can be 2 to 10 times higher than the direct transport. Notice the scale on the bottom is larger than this direct transport scale. And it's particularly during these high wind and wave events shown with these arrows that you get this additional flux and transport moving around and leading to that difference in accumulation that I described previously in the maps. Most importantly is putting this all together, and we describe in the report how we scaled up through time, but we were able to compute an estimate of the sediment delivery to the restored area here in these purple lines relative to all of the model configurations and relative to the amount of mud, which is about 50% of the total load coming through in this black line, for 3 different time periods, the 2011 through 2014, when we can compare the results to some independent measures of accumulation, mainly from elevation change, you'll see in a minute, and for the particular period of study when we were examining all these conditions in much detail, and to an average over sort of the 30-year period if the sea dikes weren't in place and all this material could have moved into the restored area. And it really shows that we're talking about, again, this sort of fraction of about a third of the material coming down the river is actually accumulating in the restored area. And so when we do scale up the mapped output of that accumulation, you know, from those 2 months of winter to 3 years of, you know, 4 to 5, 6 months of those winter conditions, you know, you start to see change occurring on par with what has been observed. So we're talking about, you know, scaling up the 0.3 to 0.6 centimeters up to, you know, a few tens of centimeters or so, which is pretty comparable to what we deduce of elevation change given very high resolution LiDAR that we had at our disposal, and some radioisotope derived accumulation rates of Judy Drexler's. Now this accumulation is just what's happening on the surface. And what's shown on the right is the change in terms of absolute elevation. And what it looks like is that we're observing erosion of this area in the net, but some accumulation on par that you see sort of over here in these model predictions. This is super exciting that it's coming together. What this means is that this sort of 14 to 30% of the river load computed to be accumulating in the restoration areas shown with this yellow field here. And what that means is that it's going to largely take upwards of 80 years to fill the volume space required to raise the grade shown here of subsided lands up to the elevations I showed you earlier for these sort of really pronounced and established marshes. This is a lot of material. You know, the question becomes, well, is there enough in the system below Alder Lake? And that's what these numbers down here show. If the entire fluvial load could be directed in and retained in this area, which would actually be robbing from other areas, it would still take about 18 or so years under present sea level. And the amount of time really starts to increase rapidly with higher rates of sea level that we assessed. This becomes concerning and leads us to whether there's enough opportunity here with this yellow identified restoration area to potentially get more sediment into the system. I'm doing a little poorly on time. So the restoration alternatives I showed you here ended up transpiring into essentially requiring this alternative C with full connectivity, full cutting of the channel down to the depth of the river channel in order to get enough hydrodynamic flow through and moving material in. And it also takes these sort of really high flows that we infrequently experience here with 2-year and 5-year flows shown with these higher sort of yellow colors with more material transport. I'm not going to go into all the details because it's in the report, but to say that these restoration opportunity here really only potentially adds about 5% more sediment to the system under these high flows today and with sea level rise. There's really just not very much additional potential. And we think it's because of the very low hydrodynamic gradient here and having to get the sediment back up onto this higher platform. And unfortunately, most of it is these sort of darker colors of fine material and not sands, which would really help build up the grade quicker. So some of the implications are from this work generally for Nisqually and generally in other locations is that restoration higher in the system is probably likely to be much more helpful to help the delta prograde over itself and have gravity move material. And it's really important to cite these locations for sediment recovery, understanding wave effects, and this idea of where the distributary is located relative to the net ebb and flood transport. And what I mean by that is the previous earlier phases of restoration on the right bank really benefit from when the river flows are flowing down and there's an ebb tide, that material can, and the flow in general through the Nisqually Reach is from left to right going out Puget Sound. There's a natural tendency for material to be able to be laid out on that right bank, not on this sort of upper drift side on the left. The sediment composition is really important. Coarser material may have greater retention if the bed stresses are high enough, and it builds elevation quicker to get the grade desired. And then the phasing. It might be interesting to explore ideas for building that grade with coarser sediment, maybe even with nourishment, to help get the marshes established as rapidly as possible, and then ensure that there's enough fines for the vegetation that they can trap, potentially before restoring tidal connectivity and the influence of waves, or also addressing ideas to help buffer those waves if the area like this is going to be exposed to wave effects. Okay, so I've got about 5 to 10 minutes max to get through the last, which is about what I've planned. The compound flood modeling gets at these objectives. How is the flood exposure of this area, the restoration investment, the I-5 and access ways, and the people and native and Nisqually tribe with assets here going to be affected by higher sea level and stream runoff? And what is the timing that I-5 and some of this infrastructure may be threatened? And if and to what extent flooding is exacerbated by the causeway itself? And are there opportunities to help reduce that flood exposure? I'm going to breeze through this, but I'll draw your attention to the channel Thalweg here in 2002, and the land cover at this eastern bridge crossing is covered with vegetation in 2002. But in 2006, 2014, and into 2020, 14 years, this meander has started to migrate upwards of 100 meters. This whole ponded area is becoming much wetter and a conduit for flow. It really begs the question whether it's setting up for avulsion, and when will that meander reach I-5? And I'll draw your attention to these lowest points of the I-5 road surface. So what we did to address flood exposure going forward, build a extension of the model up through the floodplain with an unstructured flexible mesh model. You can see the details in the report. Our validation is really exceptional. On average, less than a foot in the river, in the estuary, where we have validation data. And what we did is we examined some recent floods of record, including what you see here, the Super Bowl flood of 2020, which is about a 10-year flood event. Looks like this. I'm going to beg you to go to the report and see the wonderful map outputs and colors and the details of the flood itself. And what we did was examine how the 10-year flood and the 1996, a 25-ish, maybe more now that FEMA has redefined it, how those two floods are going to be changing with projections of increases in discharge, namely from the climate impacts group, and changes in sea level based on our Washington Coastal Resilience Project results. And what you see here for the Super Bowl flood is what we calculated for the max water depths in these blue colors. And in the 2040s, under a mean change and a high change, it quickly becomes much more extensive, deeper water. You can also see evidence of deeper water ponded behind the causeway. Similarly, for the 2080s, it just quickly gets a lot more extreme and exposed as this area is subjected to more sea level influence and the backwatering of larger and larger stream flows. We don't have to go very far to look at the change in this 25-year flood event that I showed earlier. It was extensive. People were suffering in 1996, and it just gets tremendously worse, including overtopping and flooding of the Nisqually Wildlife Refuge and a number of really important assets. And the bottom line is we computed that the 10-year event is likely to not change enough by the 2080s to affect I-5 and a number of the other infrastructure, but the 25-year type discharge event with the projected increases quickly by the 2040s and 2080s surpasses the roadway elevation in a couple areas here. And finally, some identified alternatives, literally reconnecting some of the historical distributaries that we see across the floodplain with comparable channel widths and depths and slopes through the I-5 corridor at sites 1, 3, and 5 shown here in these columns, shows that this alternative 2 flowing in this way reduces the flood sort of exposure and water depths, as well as the duration of the floods as we move out into the 2040s and 2080s, by dozens of hours per event. And this is pretty exciting because it's occurring today where it's holding back water and retarding drainage, and it will only help in the future for some time to plan a little bit more. And so in summary, sediment and waves matter for marsh resilience and function and for successful estuary restoration. We've developed some exciting new model capacity and important empirical data to help quantify the sediment budget that's needed to sustain the Nisqually marshes and inform concerns with supply, routing, and retention, which is relevant to marshes generally. Restoration siting higher in the system, and some ideas of potentially phasing with respect to different timelines for restoration objectives or outcomes, like marsh recovery. Really important to consider relative to these stressors coming our way. And some of these new ideas may help expedite full recovery. Estuary investments and these barriers to ecosystem restoration, namely the infrastructure, they're projected to become increasingly vulnerable due to climate change. And so there's going to be some activity to help reduce that today. Identifying where to do it to also help ecosystem recovery may be really important. And that's what this last bullet is, this integrated approach of modeling and assessing the impending exposure to hazards, identified opportunities for coordinated ecosystem flood management, so affecting both with the same type of effort, shown to reduce exposure, likely to enhance resilience, and are likely most cost effective because we'll be eliminating subsequent adaptive management measures. And in doing so, likely help address public will. So thank you so much. I hope you enjoyed that, and I look forward to engaging on this with you further.
Awesome. Eric, thanks so much. We do have a few questions in the chat, and so I'll just start with the first one, which was asking how much of this work could be repeated at Port Gardner. It's up in Everett, Snohomish, with its recent restoration effort, removing 3 dikes. So kind of the transferability of this concept.
The details of setting up a model, running the model, it's a large effort. I won't pretend to say otherwise. Some of the lessons learned, though, I think, are transferable fairly quickly, given some of those concepts I laid out. We have become, significantly more efficient building these models, and the computational efficiency has really improved. So it really comes down to how complex the questions are, the terrain is, some of the data availability in some of these locations. And I just invite anyone to sort of think about some of these needs. And we've been We've been talking recently about resurrecting our annual estuary workshops. We've held 4 of them in the past and took a long break, and it's time to come back and start assessing, these needs and priorities for doing such work. We do have a project in the Snohomish, by the way, and it may be covered by that.
Awesome. Yay. Yeah. Exciting stuff. And I love the steady drumbeat for resurrecting that forum. Okay. Another question. This is from John. How sensitive is tidal elevation / phase to the landward redistribution of river sediments? Acknowledging that you touched on it a little bit after the question, but thought maybe you'd want to speak a little bit to that too.
I think I understood you correctly. I hope I did. There's a detail I didn't get into, but we did see a very nice correlation with sediment delivery of that really fine fraction high up into the restored estuary with those sort of oscillating spring neap periods of highest tide and the relaxation of the tide range. It's pretty exciting, and I think we're going to advance that in a subsequent paper to explore that a little bit further. But it holds promise to then kind of applying some of what we learn more broadly quickly.
Yeah, awesome. Okay, this is from Chris regarding sediment trapped in Alder Lake Reservoir. How do we get that partially back into the system, assuming it's larger sediment at the head end of the reservoir and smaller silt at the downstream end? We're challenging. So that redistribution in the lake or distribution in the lake, and then also just releasing large sediment pulses would likely have not so great impacts on incubating eggs, knowing there's details of where the spawning is, etc. That would be important to know too. Yeah.
I'm not sure, Chris, I'm the right person to ask. Let's save that and explore it with a subgroup.
That was Chris Walbillig at DFW, by the way. I know there are lots of important Chris's in our world. Okay, this is from Sarah. What would help buffer the system from adverse effects of wave action?
That's where some sort of creative ideas are coming out, mostly in the Gulf Coast. And I think some of the Native Americans are thinking through kind of restored biological features, even just topography and berms of coarser material, a little bit more resistant to the stresses out there. But there are ideas of breaking waves a little further offshore and maybe getting just enough retention to sort of rapidly create the onset of sand accumulation. And there's other sort of artificial approaches with fencing and things like that. There could be other folks have also sort of proposed offshore aquaculture. I'm not sure that's anything that could work in such an energetic Nisqually reach, but yeah. Clam gardens, maybe sandy enough out there to do it on the tide flat. I mean,
okay. Yeah, lots to think about. This is a question from Tracy. On your second to last slide, you talked about reconnected channels. Did your work look at all at the feasibility or cost benefit of those alternatives?
Not yet. That was just some initial screening of how will the hydrodynamics and sort of projected changes influence water levels and depths. That would be the natural next step, and I think Department of Transportation is already sort of embarking on some ideas towards that.
Yeah, awesome. Oh, question from Chris. Yes. Can we get access to the recording? Absolutely. I will stick the link in the chat to check back. It usually takes us a little bit of time to process it and get it made into a movie file, but we will definitely be posting that on the Salish Sea Wiki, which is also where the final report and executive summary will live as well. This is from, God, my cat's such a ham. Question or WG says, no question, just a big thanks for the update and all the amazing work documenting restoration, its effects and future concerns requiring adaptive management. Yeah, I'll second that. Thank you so much. And then one final question, is anyone looking at implementing the restoration alternatives you explored, like alternative 2, which seemed to be the most effective?
In that last portion of the talk, or the site down along the river? The system.
I'm assuming it was in the last portion of the talk.
I think David Trout might be able to help answer this, or someone from DOT, but I think that's the kind of the next step folks are at. They're gonna kind of explore some of the designs and ideas that we had, and then maybe build off of that and look at a little bit more in detail at some of those specifics.
Great. Well, I don't see any more open questions. I just wanted to say, Eric, thank you so much. This was such a great presentation and so great to hear about the culmination of this work. Thank you so much for the presentation and the work, and we're excited to see what comes next.
Thank you for all the support, and many of you out there I can see on the participant list that have a tremendous exchange of ideas, and together we persevere.
Yeah, exactly. Well, everyone, oh, let me post the link. Sorry, I'm just not great at multitasking. Here we go.
Greg Hood raised his hand.
Greg, do you want to
Let him
write in the
talk.
Q&A what your question is?
Here, I'll let him talk.
Yeah,
Okay.
we can see.
Go ahead, Greg.
That was accidental. I was trying to find a participant list. I can't find it on my thing. Just curious, but I will say it was a good talk, Eric. I really enjoyed it, and I hope that some reconnection of distributaries occurs, because I would like to see the site, develop better than it has so far. But anyway, a very interesting talk, Eric. Thank you.
Thanks, Greg.
Thanks, Greg.
Awesome. And I just put the link to the wiki in the chat, and you can also just reach out to us and we will share it, the recording and the wiki page, if anyone has any difficulty accessing it. So with that, thanks so much, Eric, and have a great afternoon, everyone.
Thank you, and aloha Tuesday.
Take care, everybody.